Okay, so we are talking about neutralization, which is a double replacement reaction. And I have to watch time because I don't want the video to go over. So we said if I have HCl, AQ, again, I'm not writing the AQ, plus sodium hydroxide, AQ, it would double replace. So the most important thing to do is to always put the charges in. H plus, Cl minus, Na plus, OH minus. These charges come from us knowing the crisscross method, knowing how many electrons are lost. Sodium will always lose one electron. So in an acid-base, a molecule-ion attraction, we know that the ions are free moving and they're going to recombine. So we get Na goes with the Cl and simply H plus and OH minus. So this is a simple double replacement. Acid plus the base is a salt plus water. But we always have to respect the fact that when we write chemical reactions, we need to comply with the law of conservation of matter and energy. So what we have on one side, we always have to have on the other. So clearly we can just balance this by inspection and realize that we don't need any coefficients over here because everything seems to be 1-to-1. Let's try this one. These are from page 10 in the packet. H2SO4 combines with NH4OH. Okay, so assign the charges. H positive, SO4 negative 2. That's reverse crisscross. Ammonium is positive 1 and hydroxide is negative 1. You can navigate these charges through table E. Acid, base, double replace. So, isn't it true that the NH4 will combine with the SO4 minus 2? So when we do that, let's bring it over. NH4 combines with the SO4. NH4 is a plus 1, but SO4 is a minus 2. So we have to account for that. You can't lose one electron and gain 2. So we put a subscript of 2 down there to balance the charges. Now we have H and OH left behind, so we know, I'll put it down here, it becomes H plus and OH minus, which is the neutralization, that's the water. But I'm doing this quickly by inspection. You could always do the T chart that we've always done. Well, let's do it. We have reactant and we have product. Law of conservation of matter and energy tells us what we have on one side, we have to have on the other. So I have H, I have SO4, I have NH4, and I have OH. H, SO4, NH4, and OH. How many H's do I have on this side? And these are ions. 2 moles. How many SO4s over here? 1 mole. Ammonium ions, 1 mole. Hydroxide ion, 1 mole. H is over here. We only have 1, so that's a problem. SO4s, 1. NH4, Based on the chemical formula, we realize we have 2. And OHs, 1. Law of conservation of matter and energy tells us we can't start with 2 and end up with 1. The only tool we're allowed to use is coefficients. If I put a coefficient of 2 in front of there, distribute 2, and now 2 OHs. Looking good, looking good. We still have a problem here. We have to accommodate this hydroxide ion. Any ideas? Okay, I like it. If we put a 2 in front of that, we get 2 NH4s. And what happens to our hydroxides? 2. And now it looks like we're good. Balanced. 2 H's, 2 H's. SO4, 1. SO4, 1. Ammonium's 2. Ammonium's 2. See, if you don't write that salt correctly, that's where you'll get jammed. And then hydroxides are good. Balanced. Following the law of conservation of matter and energy. Acid plus a base is a salt plus water, double replacement. Okay. We'll do one more in the interest of keeping the video short. I think that we can try H3NO3, which is nitric acid plus sodium hydroxide. Acid plus a base is a salt plus water, so it's going to neutralize. We know this is +1, this has to be -1. We know sodium is an alkali metal, +1, hydroxide, -1. Double replace. So sodium is written first because it's positive, goes with the nitrate. And then the H goes with the OH. Balanced. That one's not bad at all. Okay? So I think that we're getting the idea. And I need you to practice these balancing, and we'll move on from there.